Have you ever stopped to think about how you can send your credit card number to a website you've never been to before and just trust that it's safe? It seems kind of impossible, right? Well, the answer isn't a physical vault or a secret handshake. It's actually a beautiful piece of mathematical magic. Let's break down how it all works.
So, for most of history, if you wanted to send a secret message, you needed a shared secret. A key, a codebook, something that both you and the receiver had. But that leads to this classic chicken and egg problem. How do you get the key to them securely in the first place? If someone can intercept the key, the whole system is broken before it even starts. You're basically stuck.
Right, and that traditional method where the same key locks and unlocks the message is called Symmetric-Key Cryptography. It works great if you can solve that key-sharing problem. This whole dilemma pushed cryptographers to ask a completely game-changing question. What if we could invent a lock that didn't need a shared key at all?
And the solution they came up with is it's a wild idea. It's called public key cryptography or asymmetric cryptography. The huge breakthrough was to stop thinking about one key and instead create a mathematically linked pair of keys, one key to lock the message and a totally different key to unlock it.
So this pair is made of a public key and a secret key. And they mean it when they say public. You can give your public key to anyone. You can post it online, you can email it to strangers, shout it from the rooftops, it does not matter. But the secret key? That one you guard with your life. You never, ever share it. Okay, so two keys. One's public, one's secret. I get that. But how does that actually work in practice? How does that setup keep a message from being read by, a spy in the middle?
It's actually a really elegant process. Let's say you want to send me a secret message. You'd go find my public key, which I've posted somewhere for everyone to see. You use that public key to scramble your message, basically locking it in a digital box. Then you send that box to me. Here's the cool part. The only thing in the entire universe that can unlock that box is my matching secret key.
Think of it like this. Your public key is like an open padlock that you just hand out to everybody. Anyone can take your padlock, put a message in a box, and snap it shut. But you are the only person who has the key that can open that specific lock. It's a one-way system.
Wait a second, that sounds a little too good to be true. I mean, if the public key is just out there for anyone to grab, and it's mathematically linked to the secret key, what's to stop some super smart person from just looking at the public key and figuring out what the secret key is?
And that is the most brilliant part of this whole thing. The security doesn't come from hiding the lock. It comes from making the lock incredibly, ridiculously hard to pick. It's based on the sheer difficulty of a very specific kind of math problem. The most famous system that does this, RSA, is built entirely on a branch of mathematics called number theory.
And a core piece of that is something called modular arithmetic. Now that sounds complicated, but you use it every day when you look at a clock. If it's 10 o'clock and you add 5 hours, you don't get 15 o'clock, right? You get 3 o'clock. The numbers wrap around after 12. That's math modulo 12. RSA just does that same wraparound math, but with numbers that are hundreds of digits long.
Okay, so this leads us to the absolute heart of RSA's security. It's all based on this weird imbalance with prime numbers. Fact 1, it's actually pretty easy for a computer to take a massive number and check if it's prime. Fact 2, it's nearly impossible for a computer to take the result of two huge prime numbers multiplied together and work backwards to find what those original two primes were. It's a mathematical one-way street. Easy to go forward, impossibly hard to go back.
Okay, I think I'm following. The security comes from the fact that factoring is super hard. But how do you turn that mathematical fact into an actual public key and secret key?
So, without getting lost in the weeds, here's the big picture. You start by picking two gigantic secret prime numbers. You multiply them together to get another huge number, we'll call it n. That n becomes part of your public key. Then you use your original secret primes to do some of that wraparound math, which spits out two special numbers, e and d. These two are designed to be mathematical opposites. They perfectly undo each other's work.
And those numbers become your keys. The pair of numbers E-N is your public key. Share it far and wide. But the pair D-N is your secret key. And here's the kicker. The only practical way to figure out D is if you know those two secret primes you started with. And since nobody can figure those out just by looking at N, your secret key is safe.
So what you've created is this perfect mathematical trapdoor.
Locking a message with a public key is computationally easy, but trying to unlock it without the secret key is basically impossible, because it would require solving that prime factorization problem, which could take the world's fastest supercomputers trillions of years. This idea is the foundation of almost all modern digital security.
Exactly. This system is literally the backbone of digital trust. It's what makes secure online shopping possible. It's behind encrypted messaging apps. It's how digital signatures work to verify who you are. Seriously, every time you see that little padlock icon in your web browser, this is the magic that's happening behind the scenes.
So next time you buy something online or send a secure message, just remember, your safety isn't coming from a locked door or a security guard. It's guaranteed by the profound, beautiful difficulty of a math problem. It kind of makes you wonder, in a world that runs on data, what does it mean that our entire system of trust isn't built on hiding things, but on a problem that's just too hard to solve?
If you enjoyed having your mind bent by a little bit of math, help us explain more cool topics like this. Go ahead and like this explainer, share it with someone who might find it interesting, and of course, subscribe for more. Thanks for tuning in.